Large language models have completely changed the direction of research and engineering in artificial intelligence. There are some who believe that the current language models can be categorized as artificial general intelligence, and some who don't believe we have quite reached the milestone yet. But it's universally agreed that these models are showing signs of intelligence that we have only attributed to humans until just a few years ago. In this video, I'll talk about the intuitions behind the current large language models, the science of next token prediction, and the transformer architecture. And I'll show you how to implement a language model from scratch in Python using the PyTorch library. So let's get started. First, let's try to understand what a language model is and why it is interesting to us. A language model is a type of generative model which is trained to generate text. The term generative model is often used in contrast to discriminative model. An example of a discriminative model is a dog versus cat image classifier. Such a model is called discriminative because it can discriminate between images of cats and dogs, while a generative cat and dog image model can generate images of cats and dogs. Similarly, a generative model of the English language can generate any English text. So, for example, we can train such a model on English literature, and if we train a large enough model on adequate amount of data, we can hope that the model can generate novel literary work. But that's not all. The English language is much more versatile because we can also describe math and physics and pretty much all that we know about science with the English language, which begs the question, given all the scientific knowledge so far and our observations of the universe, can we generate novel scientific work with a language model? This is an exciting area of research with many open questions to find an answer to. So let's go deeper into the science of language modeling and try to understand how we could possibly go about modeling such a complex phenomenon. To understand things better, let's start with something very simple. Let's assume we have a dice that we want to use to play a game. So each time we roll the dice, we get a number from 1 to 6. Now let's think about how we can build a model of our dice. We can use the probabilistic framework to represent the dice as follows. So here we are saying that the outcome of rolling a dice has a chance of 1/6 to be any number between 1 to 6. This model fully captures everything that we need to know about the dice. So now, instead of physically rolling a dice, we can use this model to generate numbers that follow that same distribution as the outcomes of rolling a real dice. This model is called a categorical model. There's a simple algorithm to generate samples from a categorical distribution, and it's already implemented as a function in the PyTorch library. We can simply call torch multinomial to generate samples from a given categorical distribution. So we know what a categorical model is and how to sample from it. But what if we don't know the parameters of a categorical model? How can we learn the parameters of a categorical model from data? Let's look at another example where we are trying to forecast the weather conditions. For simplicity, we assume the weather could either be sunny, cloudy, or rainy. So formally, our sample space has 3 possible states. Now we can collect data from our real-world observations of weather conditions. For example, here we have records of 8 observations. Now our goal is to use this data to create a model of the weather. Similar to the dice example, we're going to use a categorical distribution to model the weather conditions. Formally, we assume that the real weather condition has a distribution P, which we don't know. We want to use a neural network model to approximate P. Let's call our model Q. To optimize the parameters of Q, we need a loss function that measures the difference between P and Q. But note, P is not just a real number, but rather it's a distribution. So the question is, how can we measure the difference between two distributions? One of the most common ways to measure the distance between two distributions is cross-entropy. To understand cross-entropy, we first need to understand the concept of information. In information theory, information is a measure of how surprising an event is. For example, assume we are in Los Angeles, where it's mostly sunny. If we observe the weather and it's sunny, this observation has very little information, while a cloudy observation has a lot of information because it's unexpected. So it's intuitive that the information content of an event is inversely proportional to its probability. More formally, information is defined as the logarithm of the inverse of the probability of an event. Information in an event measures the minimum number of bits needed to encode that event. Now, assuming that we have a model Q of weather conditions, we can ask how surprising are the real observations to our model. This is essentially what we call cross-entropy. In other words, cross-entropy between the real distribution P and our model Q is the expected information in real observations according to our model. So the cross-entropy between P and Q can be written as the negative sum of P multiplied by the log of Q. We often use the cross-entropy to measure the difference between two distributions, and it's easy to see that the cross-entropy between two distributions is smallest when the two distributions are the same. Notice though that in order to compute cross-entropy, we still need to know the true distribution of the data, but in reality, we don't really know the real data distribution. But if we have access to samples from the true data distribution, we can approximate the cross-entropy with what's known as a Monte Carlo estimator. The estimated value of cross-entropy of P and Q is simply the negative average of logarithm of Q of x, where x is a sample from P. Now, using all that we have learned, let's try to design a neural network model to build a generative model of weather conditions. Our model is quite simple. It consists of a weight vector, W, followed by a softmax. The softmax function is a normalization function, and its sole purpose here is to map values of a vector that range from -infinity to infinity to 0 to 1 range. Softmax also ensures that the sum of all the values is exactly 1. So we can use the output of a softmax to represent the parameters of a categorical distribution. To train this model, we start with initializing the parameters W with random values. Then we take a random subset of our training data and we apply a gradient descent step to our parameters with the estimated cross-entropy as the loss function. And we repeat this process until convergence. Now let's see an implementation of this algorithm in Python. For our observations, we have assigned a value for each weather condition. 0 means sunny, 1 is cloudy, and 2 is rainy. Next, we initialize our parameters W with random values. We create an instance of the Atom optimizer, which implements a variant of the stochastic gradient descent algorithm and is one of the most commonly used optimizers in PyTorch. Then, we compute the estimated cross-entropy, which is simply negative of logarithm of predicted probability of a given event averaged over real data samples. Recall that our model is composed of a weight vector followed by a softmax. Now, instead of computing the logarithm of the softmax output, we used the fused log softmax method to do both of the operations at once. The advantage of using a fuse operator like softmax is that it's much more numerically stable. Next, we apply the gradient descent step to our parameters, and we repeat this process 10,000 times. After training, we get weights close to what we see here: 0.5 for sunny, 0.25 for cloudy, and 0.25 for rainy, which is consistent with our observations. So this simple problem can be easily solved with a categorical model. But now let's look at a much more complex problem, that is language modeling. Can we use a similar method to model the English language? To understand the challenges of language modeling, let's look at a few examples of what we are trying to model. Here are a few text samples. The task of language modeling is to generate such sentences or any arbitrary piece of text. What's immediately clear is that we can't simply model the distribution of individual words. Otherwise, our model would just spit out random words, but not a coherent piece of text. In language, we are dealing with sequences of highly correlated words. So instead of modeling individual words, we need to find a way to model the joint distribution of passages. Let's see if we can just use a categorical model to model the distribution of a sequence of words. We denote the words in the sequence as x1 to xt. For simplicity, assume we are just interested in sequences of 10 words, and assume we just have a total of 1,000 words in our vocabulary. Now, if we want to represent all the possible sequences of 10 words, we would have 1,000 to the power of 10 categories. That's a nonillion, which is not a number that is commonly used for a good reason. Just storing the weights of such a model with the current hardware is infeasible. But even if we could represent the weights, we would need many nonillions of data samples to train such a model. And the problem gets even worse if you want to have a bigger vocabulary or model longer text sequences. So this approach is not really a practical approach. Fortunately, we can use a tool from probability theory to greatly simplify our model. And that's the chain rule. So the chain rule states that the joint probability of two random variables a and b is equal to the probability of a multiplied by the probability of b given a. In fact, we can apply the chain rule multiple times to represent the joint distribution of a sequence of words as a conditional distribution of a single word given all the previous words. To further simplify this, we can prefix all our training samples with a dummy word that represents the beginning of the text. So the first word would always be a single token with a probability of 1. So this first part would be just 1, and we only really need a model for the second part. Now we can use a neural network model that takes x1 to xi as input and outputs a probability distribution over xi plus 1. This rather simple approach is one of the most widely used methods for generative modeling. Such a model is often referred to as an autoregressive model. Now let's see how we can use an autoregressive model for language modeling. Looking at the sample text here, we want to build an autoregressive model that predicts each word given all the previous words. So firstly, we want a way to represent each word numerically. This is what we call encoding. Now, to encode such a sequence, we can start by building a vocabulary of words and assign a number to each individual word. Notice that we have an extra begin token, which, as we mentioned before, we will prepend to all our data samples. Now we can represent the text like we see here. Note, however, that even though we could directly feed these numbers to our model, neural networks are actually not great at processing real numbers. So instead of feeding the number directly to a neural net, it's common to feed what we call a one-hot encoding of the number to the neural net. A one-hot encoding is simply a vector where we have a value of 1 at the index corresponding to the input number and 0 everywhere else. Given the one-hot encoding of a word, we can use a linear layer to create an embedding vector of the given word. Notice that the same word in a sequence can occur one or several times in different positions, but the embedding so far doesn't take the position of the word in the sequence into account. We can fix that by introducing another feature, which is simply the location of a word in the sequence. We call this the positional encoding. And similarly, we can use a linear layer to embed a one-hot encoding of the position. We can combine these features simply by adding the embeddings, and this would be our encoding function. Now, given a sequence of embedding vectors, we want to build a model that predicts the probability of the next word. So we need a way to aggregate these embedding vectors. Perhaps the simplest solution is to just compute the sum or average of all of the vectors. While that technically works, this is not a very powerful approach. The main problem is that as our sequence gets longer and longer, we're going to average more and more words. So we are just going to end up with a blend of many words in a single vector, and some information may get lost as a result of averaging. This is especially a problem with long sequences with many irrelevant words. So let's consider a simple modification. What if we compute a weighted average of the embeddings? This way, we can potentially weigh down irrelevant words and focus on relevant words. But how can we come up with these weights? They can't simply depend on the location of the word in the sequence, because relevant and irrelevant words can appear anywhere within the sequence. So what if the weight is a function of the current embedding? Well, that's slightly better. This way we could ignore less important words. But what is even better is if we determine the weight based on a pair of embeddings. The first embedding is what's commonly known as the query embedding, and the second embedding is the key embedding. This approach is commonly known as self-attention. Intuitively, self-attention enables a neural network to pull relevant context from the whole sequence and aggregate them together with a current word. There are several options for the exact form of the weight function, but one of the common forms is to use a dot product between the query and the key embeddings. This is also referred to as the dot attention. The paper Attention is All You Need introduced a variant of this dot attention mechanism that is sometimes referred to as QKV attention, and it's essentially just a dot attention but with linear projections on the input embeddings for both query and the key embeddings, and also a separate linear projection for the output value. These linear projections introduce additional parameters that can be learned using the gradient descent algorithm. Additionally, it's common to use multiple attention functions and concatenate their outputs to form the final representation. This is often referred to as multi-headed attention and has been shown to improve the performance of the attention models. Now I want to take a detour and talk about another very essential component of a deep neural network, and that is normalization. One of the main reasons AI models today work so much better than models from a decade ago is that today's models are much larger. We can often improve the performance of our models by making them deeper, because deeper neural network models are more flexible and better at approximating arbitrary functions. One challenge with building deep models is that they quickly become unstable. This is an area of machine learning which so far doesn't involve a lot of solid theory, but machine learning researchers empirically have found several ways to circumvent the training stability issues. One such approach is the layer normalization method, and it boils down to normalizing the features of each layer of a neural network by subtraction of the mean and division by the standard deviation of the features. The layer normalization method additionally applies a linear transformation with learnable scale parameter W and a bias parameter B to allow the neural network to produce numbers of any range. This rather simple approach allows us to train much deeper models than is possible without it. Now we are finally ready to introduce the transformer architecture. So starting from the inputs, we use a linear projection to embed word vectors and add the positional embeddings. We then apply a transformer block, which is composed of several layers of multi-headed attention, followed by MLP blocks. We also use layer normalization layers after each layer to improve the learning speed and stability. And finally, we apply a projection matrix followed by a softmax function to produce a categorical distribution over all the words in our vocabulary. And that's about it really. The transformer architecture is quite simple and elegant. Let's see how to implement this in PyTorch. We'll do this by implementing each block as a module. First, we have a two-layer MLP model that consists of two linear layers with a nonlinearity. Notice here we are using the GELU function as the nonlinearity. The GELU function is quite similar to the ReLU function, but unlike ReLU, it's smooth and differentiable at 0. Next, we have an implementation of the QKV attention model. As we described previously, we compute query, key, and value embedding vectors by applying a linear projection to the inputs. We then use PyTorch's fused scaled dot product attention method to aggregate the information from the sequence in a causal fashion. Setting the causal flag is important to ensure our model doesn't use the future words to predict the current word. This way, during training, the transformer can be trained to predict the whole sequence at once and not just the final token. This greatly reduces the training time of a transformer model. Note that we are reshaping and shuffling the dimensions of the tensors before and after the scale.product attention function, because this function requires the input dimensions to be in a certain order. Finally, we apply a linear projection to the output of the attention function. The transformer layer simply consists of a QKV attention layer followed by an MLP layer. Notice that we also use layer normalization layers before each layer. While the original paper used the normalization after each layer, some later works found moving them before would improve the results. Furthermore, we are adding the input of each layer with its output. This is what's known as a residual layer, which also improves the performance of the model. Next, we stack several transformer layers to create a deep neural network and apply them sequentially. And finally, we put everything together to create the transformer model, starting by adding the token embeddings with positional embeddings to create a representation of each token in the sequence, and then applying the transformer block, which consists of several transformer layers, followed by a final projection layer to produce the logits. We also optionally compute the cross-entropy loss if the labels are provided. This is to be used during training. Now we can use the gradient descent algorithm to train this model on arbitrary text data. Finally, given a trained model, we can use this simple method to sample from the transformer model. At each step, we compute the logits by applying the forward pass and use the multinomial function from PyTorch library to sample from the categorical distribution. Finally, we append the sample inputs and feed the result back to the model to generate the next token. In the accompanying code, we provide a more complex implementation that supports top K and top P sampling and KV caching for better control and more efficient sampling. Please refer to the code for details. We can use any text dataset to train our model. One such dataset is the Tiny Stories dataset, which is a collection of AI-generated children's stories. You can download it from the Hugging Face website. The code for downloading and pre-processing the dataset is included in our GitHub repo. I used about 98% of this data for training and 2% for evaluation. So using the provided implementation, I trained a model for approximately 2 days on the Tiny Stories dataset, and this is the result of the training. Here I'm plotting the cross-entropy loss on the test set, which is steadily decreasing, and that's what we want to see. Now, for the fun part, let's look at some samples that I generated using our model. First, let's look at unconditional generation, where we just feed a begin token to the model as input. Here, we have 2 samples from the model, which are stories that, as expected, are quite similar to the stories in our training dataset. What's interesting here is that the samples which are randomly chosen are quite coherent stories. So the model has already learned to not only produce grammatically correct English sentences, but also it has learned to generate whole coherent paragraphs. You can see that in both of the stories, the identity of the protagonist, for example, is consistent throughout the story. First one is a story about a boy named Timmy, and the second one is about a dog named Max. And throughout the whole story, Timmy is a boy and Max is a dog, which is great for such a small model. Now let's look at another example. This time we start with a prompt and ask the model to complete the text. Here I wanted to see if the model can actually answer basic trivia questions, like what's the color of the sky? It appears that indeed, for such simple questions, the model does know the answer. I have to say that I did try some basic math questions and the model miserably failed, which is understandable given that there's not any math data in our training dataset. Next, I wanted to see if the model is able to understand somewhat more complex situations. Here I'm prompting the model to complete a story about a person being trapped in a room. When we look at the completions, it's quite remarkable that the model seems to fully understand what the implications of being trapped in a room are. So the stories are all about Alex trying to get out of the room or crying for help. And that is how to build your first language model. If you are interested in the topic, I encourage you to download and play around with the code that is linked below, which provides a full implementation of training and sampling of the model that we described. You will need to have access to a GPU to train this model, but you can also run the model on Google Colab or other online platforms that provide access to free GPUs. So what we covered today in this first episode is what's known in the LLM world as the pre-training stage. Pre-training involves training an autoregressive model on raw data. To build chatbots that intelligently respond to user requests, we often fine-tune our pre-trained models using additional data with supervised learning or reinforcement learning techniques. And that's a topic that we will cover in a future episode. So stay tuned and take care.